everybody. This is the first lecture, so unfortunately the video was not properly recorded on the teaching station. So just for sake of completeness, since it's a short part of the course, so I decided to record it once again offline. So yeah, it might be a bit faster than what we had in the lecture, but I thought it's gonna be a good thing for those who could not attend the first session. So we started with the most basic example of generation. And the most basic example is the example of generating text. So basically, we want to design a model which is able to generate some text, a few sentences, maybe a paragraph or something like this. One question that comes here to mind is that why we consider this to be a basic? Well, one of the main reasons is that texts are a very specific form of modality. So this kind of data in its nature have some very nice properties. What are those properties? The first one is that they have semantics. It means that they have some meaning in them. For instance, some sentence like the honey reads a dog. This is actually not making any sense because, I mean, it's not rational that a honey reads a dog, right? It might be that I don't know, you're talking about some, science fiction story, and this makes sense in that context. But in particular, if you just think about a random sentence, it would not make a sense. And this is a very good way of thinking about language because we later on going to define the language distribution. This is going to be somehow helpful in modeling the language. So they have semantics. This means that not every sort of random combination of words is going to make a sentence for us. And another thing is that they have syntax. So a sentence like "you am perfect" is essentially wrong because grammatically it's mistaken, right? "You are perfect" was the right sentence, so it's a mistake here. So such a sentence again is very hard to happen in practice unless the one who is speaking lacks some knowledge in English. So because of these two facts, so semantics and syntax, languages are a very good model of sort of data to start with. And one point that I want to mention here is that you can always think about a natural language like English, I don't know, German, Spanish, any language that people speak. But also, this is the same thing if you want to extend your point of view. This is the same thing when we talk about programming languages, right? There we have again syntax and semantics. So like the codes should fit together and they should have the right syntax. So because of this, this is quite easy to start with text. This is like one of the start points in generative models. Now, the purpose that we have, as I said, we want to just design a model which is able to generate text. And just as a recap, what do we mean by a model? Well, I mean, you can always think of a neural network for the moment. Essentially, we want to have a neural network. But if we want to think more general, so as we had it in machine learning courses, a model is essentially a function or a mapping from one set to another. So one set is the input to the model, and the other set is what it's given as the output of the model. And this model has a bunch of parameters shown here by W. And these parameters are the one which we are able to learn, which means that they are freely tunable, and we are going to tune them through the procedure of learning. And we usually do the training procedure in order to learn, right? So it means that we start with a bunch of random weights inside the neural network or random parameters in our model. And then given the data set that we have, we go through a risk minimization problem, which going to help us find the right choices of those weights. And hopefully that model which is trained is capable of capturing the kind of pattern we were looking in the data. So this is just a quick recap on that. So as I said, if you want to think about a model, you can simply think about a simple neural network. So one neural network is a collection of neurons, and these neurons have lots of weights connecting them to each other. So essentially, all the edges in this graph are learnable, so you can choose their parameters as you wish. And typically, we have one input X when we think, for instance, about the supervised learning. And then at the output, we have some specific Y, which is the label. And we are just trying to find the right choice of ways to relate properly every X to Y, given the samples that we have in our data set. So now, if we think about the model in this way, essentially what we want to start with one incomplete English text. And then when we give it to this neural network, for instance, at the output, we're going to get the completion of this sentence. So this is what we are looking right now at, and we're gonna build upon this idea later on. So here we have a funny example. So Ali Berry is, we want to give it to the neural network, and then we want to have a very, nice sentence at the output. Doubtless the coolest prof at UofT, and yeah, what we hope for is that this sentence is meaningful, so it doesn't have any semantic mistakes, and also at the same time is grammatically correct, which means that it's somehow following the English language syntax. Okay, so now, the kind of requirement that we want, so as I mentioned, are basically semantics and syntax. So essentially, we want the output of this neural network to be to have right sentiment. For example, the kid plays with ball. This is a correct sentence semantically, but water eats the dog. It doesn't make sense because water cannot do it, right? So this is one example, one requirement that we have, and the other one is the syntax, right? So she is writing down a text. This is a correct sentence, but she am write poem. This is not correct because grammatically there is a mistake here, right? So we want these two requirements to be satisfied, and then that's essentially what we are looking for. So this idea of training a model who is capable of generating text or completing sentences, this is what we call it a language model. So a language model is essentially a model which learns from a bunch of data how to start from one incomplete text and then complete it in a coherent form. And then here, this is a very intuitive definition. You totally understand it intuitively, but there are some bottlenecks here because at the end of the day, we are going to train a model, and this means that we are going to work with some mathematical objects. Now, the question that comes up here, the first one is that, okay, how we can represent a text in form of a mathematical object, because text in like a general form is a kind of unclear definition for a neural network, right? And the other thing is that what do we mean exactly by coherence? How can we somehow define a coherent text? So these are the two things that we need to address before we get able to train this language model. So let's start with the first one, which is the fact that we want to define somehow concretely a text. So when we want to define a text, we start with the fact that one text is essentially a sequence of characters, right? For the moment, think of an English text. So an English text is a sequence of characters, right? And every single character that we have inside in English, it has finite number of possibilities, right? For instance, if we have a basic English text written by, just text, few numbers, basic formulas, things like this, then essentially we have 95 different possible choices, right? So you can think of more complicated text and the number of choices is going to get more, but at the end of the day, they are finite, right? Now, what we can say, okay, maybe we can index every single possible character with one index number. And say we have I different possible indices. For instance, in the example we had in the second item, we have 95 different possible choices. So I equals by 95 here. But in general, we could have I different possible characters in a text. And then we can just index every single character with one index between 0 and I minus 1, right? And then the thing is that we can represent that sequence of characters with the sequence of indices, right? So this is what we call it tokenization, essentially the most basic form of tokenization. And this kind of indexing that we do is vocabulary building. So what is the vocabulary here in this particular example that I said here is essentially one table like this. Here we have character. So for every single character, I'm giving one index, like the small a is index 0, capital A is index 1, and so on till the brackets to be index 93, 94. And then whenever in a text I have small a, I'm going to replace it by a 0. If I have, I don't know, right side bracket, I'm going to replace it by 94 and so on, right? So this is the way that I can just transform my text into a sequence of numbers, integers, right? And this is the idea of tokenization. So I can represent every single sentence by a sequence of character indices. And these x1 to xt, every single of them is one of the indices that I have in my vocabulary. So typically in practice, we are more interested in representing integers for the neural networks by one-hot representation. This means that, for instance, if I have one particular character, the capital A, so as we had it here in this table, when you look at it here, capital A is indexed by 1. Now say, when I am going through my text, the character at point T in my text is capital A. Then I'm going to say that its index, xt, is essentially 1. And I can represent this one by a one-hot vector, right? So I can show it by a vector, capital X, like here is bold X at time t. So this is the one-hot representation of my index. And by one-hot representation, I simply mean that only element corresponding to the index 1 here is 1, and anything else is 0, right? So this vector is of size I, in our example 95, and then its second entry here is going to be 1 because the index is 1, right? So I can essentially represent my sentence by a sequence of integers, indices, or as here by a sequence of one-hot vectors, right? And know this text is a kind of mathematical object because it's a sequence of, mathematical objects which are either scalars or vectors. So as I said, this is the most simple form of what we call a tokenization. So every single of those characters that we are separating in our sentence is one token. So it means that when I have a text, I'm just breaking it down into characters, and I'm going to index every possible character, and then I represent my whole sentence with the sequence of indices, right? So I don't need necessarily to do it in a character level. So more professional way of doing it is to do it in the word level or maybe sub-word level. For instance, if I have some word like pre-install, then I can just consider it the whole thing to be one token, or I can think of it as two tokens, right? So pre is one token, install is another token, then pre-install is actually two tokens, right? So it totally depends how I define my token. And if I want to do it, what should I do? I need to just look at the whole text that I have. So say I want to train my model on a very big textbook, then I need to go over the whole textbook and look at all possible words, for example, subwords, all possible, dummy characters, anything that I might have in this text, and then I put them into one vocabulary, into the same table as I showed you in the other slide. And then I index every single token in this vocabulary with one index, and then I represent my whole text now with a sequence of token indices, right? So this is the idea of tokenization, the process of tokenization. And one thing that you should pay attention to is that when you change the definition of tokens, the number of possible tokens you have in your vocabulary is going to change. Of course, for the case of character level, this is very simple. You're going to have a bunch of, I don't know, couple of hundreds of characters at most. But when you think of making, words or subwords to be tokens, then you're going to have much more possible tokens, right? For instance, so GPT-4 and GPT-4o, they have roughly 100,000 and 200,000 tokens, right? And this was one question by one of the students asked in the lecture. So this table that I'm showing here, this is not actually for GPT-4. So this is just, again, a dummy table here. I just want to indicate here that your tokens are no more necessarily characters or one specific complete words, right? So the could be one token, ing could be another token, maybe space could be another token, and so on. And you can think of this table for GPT-4 to have roughly 100,000 rows, and every single of them has an index. So this is the idea of tokenization. One thing that comes to your mind immediately is that this tokenization is actually a very time-consuming task. And you're totally right, because when you want to do it, you need to go over the whole corpus of data that you have. Now, I have mentioned this word corpus a couple of times up to this point. So what do I mean by a corpus? So basically the body of text that you are going to train your model on, this is what we call it, corpus. So usually when you talk about a corpus, you talk about, specific body of text, which is about, some specific thing, right? For instance, when you are training a very large model, maybe you want to train it to be able to generate, to complete scientific text as well as, uh, technical, sorry, technical text, right? Or news or financial or things like this. Then probably you're going to collect texts which are scientific and you put them inside one set. Some texts which are technical and you put them in another set. Some of them are financial, you put it in another set, and so on. Then people call each of these sets to be one purpose. And then you might have multiple corpora to do that. So, but by corpus, I simply mean the text that you have in your data set to train your model on. Now, for the tokenization itself is a kind of very, rich literature. There are lots of approaches that people can do tokenization using them. So character level is the dummy one, the one which I showed in my example. So this is the most basic one, but this is not very efficient in practice. So none of the large language models or even practical moderate size language models use such an approach. So word level is another one which is more, say, realistic to use. So it's going to end up with more number of tokens, of course, in your vocabulary because you have a finite number of characters. But when it comes to words, because each word contains multiple characters, then the number of possibilities is going to increase significantly. This is the one which many people like in early days or nowadays when they want to do like a kind of, research level practice or experiment, they might use it. But more practical ones are, for example, BPA algorithm. This is the one which has been used in many large language models. And the main idea here is that we usually do this tokenization iteratively. So essentially, you go over the whole corpus first, and then you make a very big vocabulary by just collecting all the words inside the corpus and taking them as a token, but then you're going to take a look at it and try to iteratively go over it multiple times. And each time you try to somehow merge multiple tokens together, side that those which are somehow happening so frequently together. So you're going to do some merging or maybe some separation inside this table so that the number of possible tokens is going to shrink. And by doing this iteratively, you're going to end up with a vocabulary which has significantly less number of tokens as compared to the one which you started with. Typically, this is the case. So BPE is one of the famous ones, and there are a bunch of other approaches. So since this is not a course on natural language processing, we're not going over them, but if you're interested, you can take a look. I have put some extra readings for you if you're interested to read about that. So now let's talk about what's going to happen after tokenization. So once we have done the tokenization, whatever the text we have, this is going to be a sequence, right? We either can show that sequence by integers or their equivalent one-hot vectors, right? And we do know that if we want to fit it into a neural network, we essentially need to have a vector, right? And if we want to give that vector in this one-hot form, every single of these vectors is going to be of dimension I. So I told you for GPT-4, this is 100K, right? For GPT-4o, this is 200K. This means that every single of these one-hot vectors is going to have roughly 200,000 dimensions, right? Now, this is going to be too much, right? So in practice, it doesn't make sense that we work in a 200,000 dimensional space because this is too much. And one other point that we can notice is that whenever you add one extra tokens to your vocabulary, you're increasing one dimension, which is again not a practical thing, right? So it's a huge dimension and it's obvious that we don't need it, right? And it's very ad hoc to the number of tokens that we have inside our vocabulary. So we typically do one step further to represent our sequence, and that is the idea of embedding. So what do we mean by embedding? Well, once we have done the tokenization, we can represent that vocabulary, the table I showed you, in the form of a dictionary, right? So this vocabulary or this dictionary basically just has the token, for example, the subword or the word that I have, the word like apple. And then here is the index of apple, the word apple inside my vocabulary, right? And I have in general different tokens, right? Now, one thing that I can do after this is that I can represent every single token here. Instead of showing it by an integer or by an index, I can also connect one vector to this. And this vector, which I'm showing it by bold X here, so whenever I show something by bold, I'm talking about a vector. So this vector X here is essentially e-dimensional, and this dimension E is fixed, so I'm not going to change it even if the number of tokens in my vocabulary is changing. Now, I can correspond every single X to one real valued e-dimensional vector. And essentially, since I'm working in the real domain, then it doesn't matter what E is. I can always have as much as vectors as I want, right? So I can always represent them with these vectors. So this is the idea of embedding. So essentially, embedding is nothing but adding a vector, also a unique vector, in addition to the index to every single token that I have in my dictionary. Now, mathematically, if you want to think about it, embedding is nothing but doing a linear transform on the one-hot vectors that we have or for the representation of the tokens, right? How we can say it? Okay, let's say that I am working with index x. Now, this x is a number, as I showed here, between 0 and I minus 1, right? If you want to think about our previous example, this is something between 0 and 94. Now, if I want to find out what is the embedding of this index x, what should I do? Well, I can show everything with a matrix, all the embedding vectors with a matrix E. So this matrix E is something of this form. So as you can see here, every column of this matrix is one embedding vector, and that embedding vector is e-dimensional, okay? So I have I different of them. So this matrix E has E different columns and I different rows because every single of these guys has I different rows, right? Sorry, E different. Sorry, once again. So this guy has I different columns because we have I different tokens, and it has E different rows because every single of these guys has E different entries, right? And now what I want to do, I want to find what is the embedding of X. So I'm going to go and select the guy who is at column X, right? So this is going to be my embedding, right? But this is the same as multiplying this whole matrix E with this vector, which is 0 everywhere, but at entry X, right? Well, this is same as doing this linear multiplication, right? So I'm going to get my matrix E. This matrix, as I said, is collecting all possible embedding vectors. And then I multiply it with the one hot representation of my token, right? So essentially what embedding is nothing but multiplying the embedding matrix with a one hot representation of the token. And this is something that we can always easily do by neural networks, right? Or by a simple linear layer, right? So to understand the whole idea, let's just do one simple example. So say our corpus is this toy corpus, the title, the good, comma, the bad, and the ugly. So this is a name of an old movie. And now if you want to just represent this guy as a mathematical object, the first thing we need to do is to just do the tokenization. And for that purpose, we need to build a vocabulary. So how can we do is say we are just doing a very naive form, uh, word level tokenization. So we essentially start with the. So the is going to be the first token. Then this next token is good. So next one, I'm going to put comma to be one token. And then the next one is the, which already exists in vocabulary, so I don't need to put it anymore. And then bad does not exist in this vocabulary, so I'm going to add it. And does not exist, I'm going to add it here. The, again, exists, so I'm not going to add it. And then finally, I have ugly, so I'm going to put ugly here. This is my last token. And then I'm going to put some index for them. So it's going to start from 0 to 5. I have 6 different tokens, right? Now, if, for instance, I want to represent the word and in a text after making this vocabulary, I can either represent it by index 4, which is the index of my token here, or for neural networks, I can represent it with one hot vector, right? So this is going to be one 6-dimensional vector, and only entry 5 is 1, anything else is 0, right? Now, for instance, if I want to just represent this whole title by the indices, I can simply put the indices here, right? 0, 1, then 2 here for comma, then 0, then 3, 4, 0 again, and then finally 5, right? So this is the way that I do the tokenization. I use my vocabulary here, and then I represent this whole sentence using the indices, right? Well, then now let's say we want to do embedding. And for embedding, for now, say I'm just giving you one dummy example. So I say that, well, I want to just do this kind of embedding. So this is the embedding matrix E. And the first column here, so think about this column here, this guy here. This is the embedding vector for the first token. So this is the first token, right? So this is index 0, and this is its embedding vector, right? So whenever I see I'm not going to show it anymore by 0, but I'm going to show it by this 2-dimensional vector. Or for instance, whenever I see comma in my text, I'm not going to show it by index 2, but I'm going to show it by this vector, right? So this is the idea of embedding. This is the embedding vector for this one is the embedding vector for token this is the embedding vector for token token end. And yeah, that's it, right? So now, say that I want to I can essentially represent this vector here, or this embedding of the tokens in the whole vocabulary into the form of a visualization in two-dimensional space. So say that I have this two-dimensional space here. This dimension, the first, like the horizontal dimension, is showing the first entry, and the vertical dimension is showing the second entry. Okay, so for the word D here, as you can see, this is located at 0 0.1, 0 0.1. So I can show it as a point in this two-dimensional space, right? For the word good, it's located at 1, 1. So I can show it at the point 1, 1, and so on for a comma and anything else inside this dictionary, right? So essentially, any token that I have could be visualized as a two-dimensional point in this embedding space that I have. And it doesn't matter how many words I have in my vocabulary, I can always show, like, pack my two-dimensional real space with as much points as I want, because this is a real space. Theoretically, it has infinite number of points in it, right? So this is why I can simply go for a fixed number of dimensions, but you can guess that in practice, I cannot, like for a very practical language model, I cannot stick to two-dimensional space. I definitely need to increase my dimension to thousands, but it could be essentially much smaller. And this is in practice the case, that this is much, much smaller than the number of tokens I have in my vocabulary. Now, a few notes here about embedding. So one note here is that typically what we do with embedding in practice is that we treat it as a kind of learnable parameter. So the embedding vectors are somehow generated initially randomly, and then we're gonna leave them to be trained through the whole training process, meaning that every time that we forward pass over our neural network, and then we do the back propagation and compute the gradients, we also compute the gradient with respect to those embedding vectors. And then we update with a specific learning rate, we update those embedding representations, right? So this is a good idea, because this is going to essentially help us having a sort of semantically grouped embeddings in practice, meaning that if we start with random points in this two-dimensional space, gradually after training, the words which have same functionality or meaning, they are going to somehow group together. For instance, ugly and bad have the same sort of meaning in this context that we are working with, then they are going to be close to each other, right? So this is exaggeration in this diagram, of course, and this is totally dummy diagram. Just wanted to give you the idea here. Or for instance, these other words like the and comma, they have a sort of same functionality in our text. And because of that, they are going to be maybe close to each other, and good is just giving another meaning, so it's going to be somewhere else. So this training or learning of the embeddings is going to benefit us in this respect. So that being said, we are pretty much over with this part. So last thing, okay, we do know right now how we can represent a text as a mathematical object, right? So one text for us is a sequence of tokens, and those tokens can be either represented by their indices, or they could be represented by their 100 representation, or better in practice, they could be represented by their embeddings, right? So we can make this definition of language model a bit more formal now. So what we can say, we could say, okay, we have a sequence of tokens, which is incomplete, that is, or incomplete text, right? And this sequence of tokens is coming from specific vocabulary with I different possible tokens. And the thing that we want to do, we want to complete this sequence, meaning that we want to just add a bunch of other tokens after this sequence of T tokens, right? So maybe we have T tokens here, as you can see. And then the thing that we want to do, we want to add L extra tokens after that. And what we want from those tokens, we want them to be coherent. meaning that when they sit next to each other and when we decode it, we get back the original words represented by those tokens, then the sentence reads well in the English language, right? So this is what we are looking for. So now we do know how we can represent a text as a sequence of tokens, but we are still unclear about the meaning of a coherent sequence. This is what we are going to talk in the next session.